Have you ever hit a wall in a math problem where your variable, the x you're trying to solve for, is trapped way up high in an exponent? It feels like it's totally out of reach. Well, in this explainer, we are going to show you the special tool that's designed to solve that exact problem. And this is just a perfect way to think about it. All your standard algebra tools, adding, subtracting, multiplying, they just can't get up there. They're stuck on the ground floor. So to crack these kinds of equations, we need something special, a kind of mathematical crane that can reach up and lift that variable right down to our level. And that crane? Well, it has a name, the logarithm. This is the one tool that was literally designed for this very specific, very crucial job. It's the key that lets us unlock these otherwise impossible exponential equations. This right here, this is the engine of our crane. The power rule of logarithms is the real hero of our story today. It's the magic trick that lets us grab that power p from inside the logarithm and just move it right out front as a simple multiplier. This is the one move we're going to use again and again.
Now, the best part is, this isn't some random guesswork. There is a super reliable 4-step procedure that's going to work every single time. Just think of this as your blueprint for success. Here it is. Step 1, and I cannot stress this enough, you have to get the part with the exponent all by itself, isolated. Then, step 2, you take the natural log of both sides of the equation. Step 3, you bring in the crane, use that power rule to bring the exponent down in front. And finally, from there, it's just regular old algebra to solve for your variable. All right, theory's great, but let's see this thing in action. Let's get our hands dirty. We're going to walk through 3 examples, starting simple and then leveling up, just to show you how powerful this 4-step plan really is. So let's start with a classic. We need to solve for x, where 5 to the power of x equals 12. And you'll notice step 1, isolating the exponential, is already done for us. The 5 to the x is all by itself. Perfect. So we get to jump straight to step 2, take the natural log of both sides. Then, step 3, the power rule does its thing, and that x comes right down in front. Now we just have x times the natural log of 5. To get x by itself, we just divide both sides by the natural log of 5. Easy as that. You punch that into a calculator, and what you get? About 1.544. And that is the exact power you would need to raise 5 to get exactly 12. Okay, time to wrap it up a little. This time we're solving for t. Now look at this equation. We've got a 3 multiplying our exponential term and a 5 being added on. This is where step 1 becomes absolutely critical. We have got to clear the area before we can bring in our logarithm crane. So first, we subtract 5 from both sides, which leaves us with 9. Then we divide both sides by 3. And there it is. E to the power of 2t equals 3. The exponential is now isolated or ready to go. Okay, now we just follow the plan. Take the natural log of both sides. And here's a really neat shortcut. The natural log, ln, and the base, e, are inverses of each other, so they just cancel out. That leaves us with just the exponent, 2t. From there, it's a simple division. And we've solved for t. So our final answer is the natural log of 3, all divided by 2. Which comes out to roughly 0.549. See? You follow the steps, you get the answer. All right, get ready, because this is the advanced challenge. Now, at first glance, this equation just looks like a total mess, right? But believe it or not, there's a secret hidden inside. It's actually a problem you already know how to solve. It's just wearing a very clever disguise. The trick here is a technique called substitution. We're going to do a little switcheroo. If we let the letter u temporarily stand in for e to the x, then that means e to the 2x is just u squared. And suddenly, poof, our messy exponential equation transforms into a simple quadratic. And we've all solved those before. This one factors beautifully. So this gives us 2 possible values for u. U could be 5, or u could be -1. But wait, we're not done. We need to solve for x. So we substitute back. In the first case, e to the x equals 5. We solve that just like our first problem. X equals the natural log of 5. Done. But in the second case, e to the x equals -1. And that, my friends, is impossible. You can't raise a positive number to any power and get a negative result. It just can't happen. So we throw that solution away, leaving us with just one true answer. Now, let's just pause for a second and talk about the single most common mistake people make with these problems. It's a really easy trap to fall into, but once you know what to look for, it's also really easy to avoid. Look at the wrong way on the left. If you jump the gun and take the log before you isolate, the power rule can't help you. That x only applies to the 5, not the 2. So it's still stuck. You've hit a dead end. But on the right, we do it correctly. First, we divide by 2. We isolate the 5 to the x. Remember, always isolate first.
Okay, so we've mastered a pretty neat precalculus skill. But you might be asking, why does this actually matter in the real world? Well, as it turns out, this exact math is used in some pretty high-stakes situations. Seriously, how can solving for a variable that's stuck in an exponent actually help solve a crime? The answer is surprisingly direct and honestly pretty cool.
You see, forensic scientists use a principle called Newton's law of cooling to determine a time of death, and that law is a classic exponential equation. The variable they need to solve for is time, t, and just like in our problems, it's stuck up in the exponent. So what do? They follow the exact same procedure we did in our second example. They isolate the exponential term, and then they use the logarithm crane to solve for t. This isn't just a problem in a textbook, it's a tool that can help deliver justice.
So what starts out in a precalculus class clearly doesn't end there. We've just handed you the keys to the logarithm crane. So now I ask you, what other complex problems could you solve with it? Think about things like population growth, or radioactive decay, or how your money grows with compound interest. The applications are absolutely everywhere, just waiting for you to unlock them.